SwayamPrabha. Digital India. Educated India.
Hello, I welcome you all in this course on refrigeration and air conditioning. Today we will continue with psychrometric processes, and this is the last lecture on psychrometric processes. Today we will be covering evaporative cooling, winter air conditioning with recirculation, winter air conditioning preheating with exhaust air. Now all these measures, recirculation, preheating with exhaust air, these are the measures taken in order to save energy in air conditioning system. Before we start, because we are doing a lot of mixing in air conditioning systems, so I should repeat the concept of mixing, that if there are two stream at state 1 and state 2 and they get mixed, right, and the length mixed and we get the state 3, and this length is A, this length is B, then M1 by M2 is equal to B by A, reciprocal of this section. Or on a psychrometric chart, we can take in terms of temperature also. This segment A is T3 minus T1, segment B is equal to T2 minus T3, or in specific humidity, in the form of a specific humidity. In previous lecture also I explained you this. Now the benefit of mixing, as I told you earlier, is regarding the saving of energy. So in a psychrometric process, the moment we mix the two streams, the saving of energy takes place. For heating, we consider two cases where the mixing, this was the return air, this was the supply air, and mixing took place, and then heating, and then this is return air and then heating, and this is room load line. This heat is attained in this is state 1, state 2, state 3, state 4, state 5. This heat is attained inside the room. Now mixing, this is the mixing of exhaust air before the cooling coil. It means this is the cooling coil and this is room, and air coming out of the room is mixed with the exhaust. In one of the cases, if you remember that here also we mixed, and part of the air is also mixed after the exhaust coil or after the heating coil. Now if it is mixed after the heating coil, then the point mixing will take place between 5 and 1 and the point will lie somewhere here. In some of the system, heating coil is not there. For example, small capacity system, split air conditioners, heating system is not there, and they have certain bypass factor, and air is directly supplied to the room after the cooling coil. And here if the mixing takes place after the cooling coil, split air conditioning, there is no mixing at all. Return air is mixed with the fresh air, it is here, not here. But in a duct type of system, if mixing takes place after the cooling coil, the position will be somewhere here. We will solve some numericals on actual air conditioning system. When we will solve those numericals, the concept of this mixing will be more clear to you. Now second thing is bypass factor. Now suppose I want to have this state for cooling and reheating. So one possibility is this when bypass factor is 0. Another possibility is this when bypass factor is, let us say, 0.1. Then will supply air temperature will rise a little. Another possibility is when bypass factor is 0.2 or high bypass factor, then air will be at relatively higher temperature. State A, B, C. A is the case when bypass factor is 0. then bypass factor, let us say bypass factor is 1.1, we will be getting B. Higher bypass factor we will be shifting on this side, but it does not mean that we are saving energy when we are shifting this side, because when we are here, then this much heating is required. When this point is shifted to this point, only this much heating is required. When this point is shifted to this point, only this much heating is required. And this is the supply air, state of supply air. Say when the bypass factor is increasing, we are getting P, suppose Q and R. The temperature of R is definitely lower than the temperature of P. Suppose this temperature is, let us say, 15 degrees centigrade, and this temperature is 10 degrees centigrade, right? Outside temperature is same, return temperature or mixing temperature is same, or if we are taking 100% outside air, let us take example of 100% outside air. So if we are taking 100% outside air, this is supply, 100% outside air, 100% outside air and 100% outside air. This will be shifted to ABC. So if you are taking 100% outside air, in that case also, or it is a mixture, this coil temperature is reducing if we are increasing the bypass factor. It means the temperature difference between condenser and the evaporator is increasing. When this temperature is increasing, it means we have to increase the capacity of the plant, or in a nutshell we can say, for same type of cooling effect we have to spend more energy. So bypass factor is not a welcome type of thing. Bypass factor should be as low as possible. In order to reduce bypass factor, the number of rows of the coils are provided, that increases the fixed cost of the equipment, but the recurring cost goes down, because in this case energy consumption is less. So these two things I wanted to clarify, because it appears from this diagram that if you have higher value of bypass factor, you can save energy in the heating of air, but that is not the case. Ultimately you will end up in paying more for the energy consumption. Now evaporative cooling system. In evaporative cooling system, as all of us know, there is a washer and air is blown over the washer, and when the air is blown over the washer, the air follows the constant wet bulb line. Suppose air is available at state 1, it goes up to state 2, and after taking load it may attain state 3. But this process 1 to 2 is evaporative cooling and it follows the constant wet bulb line. There is a efficiency for evaporative cooler also, and that efficiency is this actual temperature drop and that maximum possible temperature drop. This is known as effectiveness of evaporative cooler, because in evaporative cooler we never get 100% saturated air. Okay, we may get 90% or 80% saturation of air. In that case, the effectiveness of the evaporative cooler will be this temperature drop divided by maximum possible temperature drop. Now we will take winter air conditioning. Now winter air conditioning, heating has to be done, and as I explained earlier during psychrometric processes, if the heating is done, suppose this is something 10 degrees centigrade. When the heating is done, sensible heating, if you do sensible heating, the relative humidity will decrease. This is maybe, say this is 70%, so this may reduce to, let us say, 30%. We keep on heating the air, the relative humidity will keep on reducing, however the specific humidity will remain same. So while cooling, we have to increase the humidity also. So how we can increase the humidity? There is only one way of increasing the humidity, is add some air, and add some water, and water can be added by adding the by putting the air washer on the circuit. So the process can be like this. Initially we may heat, Suppose this is the initial state. This is initial state. So, initially we may heat and then it is passed through the evaporative cooler and then again reheating. In this case, we can get, so heating, evaporative cooling and then again heating. So, in such by following this path, we can attain the final state. Now, this can be done in more stages, but that will increase the cost of the system, that evaporative cooling, then heating, then evaporative cooling, and again you are getting this state. Because in heating, the moment you start heating the air, the relative humidity starts reducing. So, definitely water vapor has to be added in the air so that humidity is maintained. The same type of process we will draw on psychrometric chart. So, here we can take some temperature, let us say outside air is available at 8 degrees centigrade or 10 degrees, let us take 10 degrees centigrade, and relative humidity is 20%, it is dry air at 20 degrees centigrade, and we have to come here 25 degrees centigrade. I explained it earlier also that we are taking this 24 degrees centigrade temperature and 50% relative humidity as supply condition for the sake of convenience only. Otherwise, in a normal air conditioning system, the supply temperature is less than this. Only then we can get temperature in the air after picking heat in the room. We can get temperature of air approximately let us say 24 degrees centigrade, and the temperature of air leaving the room may be at 26 or 27 degrees centigrade. So, here we will come back to the this heating process. So, 10 degrees centigrade and 20% relative humidity, the air is heated. Air is heated, air can be heated up to, let us say 35 degrees centigrade, right, and after heating 35 degrees centigrade, evaporative cooling can be done. We can follow this constant wet bulb temperature line, we will follow this constant wet bulb temperature line, and then from here the heating can be done, right. So, the entire process is like this. So, the entire process is like this, from state 1 to state 2, state 2 to state 3, state 2 to state 4. Suppose air is available not at 20% relative humidity, let us say 40% relative humidity. Same dry bulb temperature and 40% relative humidity. In that case, less heating will be required, and we can again take this constant well bulb temperature line and we can come here. We can heat the air up to this is a designer's choice, we can heat the air up to this point. If you are heating air up to this point, then you will have to follow this line and then heating. Now, the question is, can't we heat the air up to this point so that there is no reheating is required? We can heat the air up to this point. I will draw this on the board, then things will be clearer to you. In a psychrometric process, when the weather is, outside weather is cold, then heating, following the evaporative cooling, and then again reheating. Now 1, 2, 3, 4, and we are getting this state. Now, instead of going up to here, if we heat up to another temperature, let us say temperature 3, and then we can heat and we will be saving some energy here. Further, we can further heat up to here and then do evaporative cooling. So, which process we should adopt? Should we go for this process, and this process? Now, if you notice in this process, the air which is emerging from heater is on higher temperature, air which is emerging heater is from lower temperature. So, this process 1, 2, 3, 4 is confined to the low temperature, right. The moment we are shifting on this side, high capacity heaters will be required. Now, high capacity heaters will have, right, definitely will consume more energy. So, definitely this is a preferred process 1, 2, 3, 4 in this case. If we go up to this, from here you can see we will have to heat air up to 40 degrees centigrade, and after 40 degrees centigrade it will go for evaporative cooling. So, unnecessarily we are adding this heat and we are then removing the heat. So, this can be avoided if we judiciously choose a path which can provide minimum energy consumption in attaining final state from the initial state. Now, last one is winter air conditioning preheating with exhaust air. Now, exhaust air coming from the room. So, if we draw a circuit for exhaust air, winter heating, then we will start with the exhaust air because heating with exhaust air is taking place. So, this is load line, let us say 1, 2, this is exhaust air, it is getting mixed with the outside air, 3 is outside air. So, it means at state 1 the air is entering the room and state 2 air is leaving the room. This air gets mixed with the outside air, and then after mixing the heating takes place, heating, evaporation and then heating. Now, if we want to display this process on psychrometric chart, let us assume outside air is at 6 degrees centigrade. So, 6 degrees centigrade air is mixed with the exhaust air. Suppose exhaust air is available at 18 degrees centigrade or 18 degrees centigrade and 50% relative humidity. So, this is the load line. Mixing, let us say 50-50 mixing is taking place. So, 50-50 mixing means 50% of this and 50% of this. I am just taking approximate value. This is the mixture, state of the mixture. Now, this state of the mixture shall be again heated and the same process will follow. If we want to show this on a schematic diagram, then the diagram shall be like this. Initially, there is a heater, there is a duct, it has dampers and a filter. Then there is a heater which is heating the air. After heater, there is a washer, there is air washer. After air washer, again there is a reheater, and after heater, the air is supplied to the room. Air is supplied to the room. Now, air coming from the room, this is again through a duct, and this part of this air is mixed with the supply air, as we did in the case of summer air conditioning. In summer air conditioning, the cold return air was mixed with the hot air in order to save energy. Here, relatively hotter return air is mixed with the cold outside air for the purpose of heating of the system. Because these air conditioning systems, they are centralized air conditioning system and they consume a lot of energy. And these mixing processes are all energy saving processes. So, these processes allow us to save energy while doing air conditioning of the building. Now, we have completed almost all typical air conditioning processes in summer and winter air conditioning processes. We have covered the hot and dry weather, we have covered hot and dry and hot and humid weather, we have covered the winters, in winters, and we have covered the preheating of the air with the winter during winter and with the exhaust, and for the summer pre-cooling of air with the exhaust. Now before I end this psychrometric processes, I have forgotten one process, that is chemical dehumidification. In evaporative cooling, the vapor is used for, the water is used for the cooling purpose, and evaporation of water brings the temperature down. This is during evaporative cooling, state 1 to 2, and this line follows the constant well bulb temperature line. Now this is possible only in the case when temperature of water is equal to temperature of wet bulb temperature or temperature of the wet bulb. If the temperature of water which is being used in this process is less than the temperature of wet bulb, we will be getting this line. If temperature is more, we will be getting this line. So it is always stated that during evaporative cooling, the process follows the wet bulb temperature line, but wet bulb temperature line can only be followed in the case where the temperature of water is equal to the wet bulb temperature. Otherwise, there is going to be a deviation. If temperature of water is less, this line will be followed. If the temperature of water is more, this line will be followed. But since these lines are very close to each other, the difference is minimal, very less. So even if there is a difference in the temperature of air and cooling water, it can be taken as the following the wet bulb temperature line. In some of the psychrometric charts, you will find that wet bulb temperature, there is no deviation in wet bulb temperature line and constant enthalpy line. So there in those charts you can comfortably follow the constant enthalpy line for adiabatic cooling. Another process which I forgot to tell you is adiabatic dehumidification. In case of adiabatic dehumidification, it is reverse of, suppose outside air is at 40 degrees centigrade, and this is adiabatic humidification. Now if the process takes place in reverse direction means in this direction, then this is known as adiabatic dehumidification. This process is taken into account when the temperature and humidity both are high. Suppose there is a air available at 21 degrees and 19 degrees centigrade, but the humidity is very close, it is close to 100%, 95%. So such type of air supply is also not recommended. So very high humidity if I want to reduce, then this adiabatic dehumidification process can be adopted. And here in pH diagram, in the psychrometric diagram, it can be shown like this, following the constant wet bulb temperature line. Now adiabatic dehumidification is done with the help of chemicals. These chemicals, they do absorb water from the vapor, and the water vapor is associated in these chemicals, they become wet, and it is associated with these chemicals in the form of like silica gel. So if you put the silica gel in moist air, the silica gel will absorb the water, and in this process the latent heat of condensation is liberated, and due to this latent heat of condensation, the heating of the air takes place and the temperature of air rises. So it is reverse, it is almost reverse of evaporative cooling. In evaporative cooling, due to evaporation of water, there is a drop in temperature. Here, due to condensation of water, there is a rise in temperature of air. So this process is also very useful in the case when the humidity of the air is very high. Now I think I have completed almost all processes, typical processes in air conditioning. I have completed psychrometric processes for the cooling during hot and dry summer or hot and wet summer. I have covered the psychrometric processes for adiabatic humidification, adiabatic dehumidification. I have covered the winter air conditioning with recirculation and through air exhaust. But we should remember that in air conditioning processes, two things are important while designing a system. That one is bypass factor. Bypass factor should be as low as possible in order to save energy, and wherever is possible, we should take advantage of waste heat or waste energy so that net energy consumption in the system is minimum. With this, I conclude my today's lecture. From the next lecture, we will take up the infiltration in the buildings. Thank you.